I want to give an update on some commissioning and calibration we've been doing for the NIRISS SOS multi-stripe subarrays. So some of you might remember from last year, we had JWebbinar 43 where we introduced this capability, and it was open for cycle 5 proposals. And then over the last few months, particularly, we've been trying to calibrate and commission the mode on Sky. So yeah, hoping to mainly give you an update of that, where we're at, and let you see really kind of how good things are going. First off, I just want to give a bit of an overview of the capabilities for those who aren't familiar. So NIRISS, particularly NIRISS SOS, this single object slitless spectroscopy, leverages this GR700XT GRISM. And the idea is that you can disperse the light from a single source into these 3 spectral orders. And here's our nominal subarrays below that were available right from launch. And this covers this kind of 0.6 to 2.8 micron range. Now, really, SOS is a workhorse mode for transiting exoplanet science. There are some programs that are branching out a little bit, but I would say most of our observations focus on this. So you can see some examples here of WASP-39b, TRAPPIST-1c, WASP-17b, and many more proposals on top of that. So for cycle 5, we introduced these 4 multi-stripe subarrays for NIRISS SOS. And the idea is that they cover an identical detector footprint to the substrip 256, which is the standard subarray for SOS, using the superstripe implementation of multi-stripe. Now, I mention this because there is some subtlety. There's a difference between how DHS implements multi-stripe and how SOS and PRISM implements multi-stripe. So really, I'm going to use these interchangeably, but I'll provide some documentation towards the end if you really want to go and understand what substripe means and what superstripe means. And particularly the old JWebbinar will be a good reference for that as well. Now, for SOS, we're able to really dramatically improve the bright limit all the way down to a J magnitude of roughly 3.5, and that's for our smallest stripe size in this sub-17 stripe, where the number here is kind of indicating how many pixels wide the stripe is. And that covers all the known transit hosts that we know of. So really anything should be observable with SOS at this point. So it splits our standard subarray into these stripes, and then the subarray name encodes the size of the stripe. And then the way the observation will happen is that we will move throughout this nominal stamp size, perform one integration on a subsection or stripe of the subarray, complete that integration, and then move to the next one. And then when that's done, we complete that and move to the next one until you've filled out the whole original subarray. And then we will repeat the process. So it's slightly different to the regular readout, but that's generally the format. And this is really what improves that bright limit. We're reading out less of the detector, so we can do it much more faster. And that means we're not going to saturate as quickly. So that's really all I'm going to do in terms of description for superstripe, because we have plenty to cover in terms of calibration. But yeah, I really want to point you to JWebbinar 43 if you want to learn more about how it works in general and how to implement it yourself. Okay, so calibrations. We had a few programs planned, all conducting kind of throughout June and July. And here's the kind of table of what's going on here. So I'll just go through it slowly. So our first calibration is just an initial check on the functionality and performance of the subarrays. And that's just a quick 2-integration, 2-group exposure for all of the substripe subarrays, just to make sure they all work. Beyond that, we conducted some darks. We conducted some flux monitoring with the absolute calibration. This is to do our photometric standard and catch all of the photometric calibration we want to do. Because this is a brighter mode, we also wanted a brighter photometric standard. So that goes all the way to JF 5.7. And then last but not least, we have this transit observation we're conducting of WASP-18b. This is kind of a 10 Jupiter mass source we'd be observing in transmission to hopefully get a close to flat spectrum using the multi-stripe mode. And then we've also paired that with not quite simultaneous, but close in time wide field camera 3 observation with HST. So we get a nice comparison close in time to see if any systematics or signals are repeated across the two, and everything kind of stitches together nicely. So the first one, the bright photometric standard, that's wrong, sorry. The test of these initial subarrays is as follows. And the main question really was, would this work when we put it on sky? And the great answer is really it does work. So you can see here, this is an example for sub 680 stripe. And I want to point really to the right-hand side here. You'll know that we interleave these reference pixels between the stripes, and you can see that here. Each frame here is representing a different stripe, and you can see the columns on the right don't contain any flux from the source. That's because they're those reference columns that we're using. So really, this was a nice sign that everything was working. And we repeated that, like I said, for all 4 stripes. It's just a quick 2 integration, 2 groups exposure for each one, and all of them worked well. So no issues there. You might be seeing some elevated noise as you go towards the smaller stripe sizes. That's nothing to worry about. As you go to smaller stripe sizes, a single 2 group, 2 integration exposure is just going to have a shorter total exposure time overall. So the noise is reflective of that, really. And importantly as well, this is all processed through the JWST pipeline. So on the previous frame, I was showing you that default, how the data comes in, it's chunked up in these different files, but the pipeline itself will reconstruct everything for you into the regular subarray dimensions. So if you have a pipeline of your own that kind of operates on standard data, you should be able to run it as normal with the SuperStripe products. We also checked the photometric calibration just between the stripes themselves rather than any sort of absolute calibration. And all of the spectra seem to agree quite nicely. Again, the noise is increased because of the different frame times. And I also want to point here, we have order 1 on the top and order 2 on the bottom. The flux kind of starts shooting up here towards these longer wavelengths for order 2. It's quite a known effect for SOS, really. The throughput and the photometric precision at those wavelengths is really quite low. So it's not unusual to get kind of poor performance out there. And really 0.6 to kind of 1 micron is really the range where we say SOS order 2 is best operated at. And that's kind of nice because beyond there, you already can pick up from order 1 anyway. Okay, next was a quick check of interstripe systematics. So this is one thing I certainly was a little concerned about before we had any observations on sky. Well, what we're looking at here is just a subsection of the wavelengths from the order 1 spectra for all of these substripe subarrays. And you can see here that I've marked the edges of the stripes, these dash gray lines. And the broad conclusion you can see is that there isn't any kind of discontinuity or anything between the different stripes. And it looks like the spectra are well extracted, and we don't see any strong systematics between stripes that might affect any kind of scientific interpretation. We are planning some more investigation on sources that are a bit more saturated that might have some kind of charge bleeding effect. But thus far, we really haven't seen any kind of issues with this. And then finally, are we meeting the expected signal to noise? So again, just from this 2 group 2 integration exposure, we find we're meeting a prediction from the ETC in these black lines here compared to the individual stripe measured signal to noises quite well. We're kind of within 10 to 20%. I will note that you might see some small improvement at these longer wavelengths. I think that is primarily due to residual background. These exposures didn't actually have a background subtraction. And that can make a small difference for the assumed SNR. And then the shorter wavelengths, you can see we're actually getting a modest improvement for the larger stripe sizes to a kind of small kind of negative difference for the smaller stripe size. That's still under investigation. But in terms of cycle 6 and preparing proposals, you should be confident that you're getting equivalent signal to noise to what we actually observed on sky. Okay, next up, the darks. Just quickly, we have dark observations were taken, and they are broadly consistent with our substrip 256 dark. This is definitely work that's still ongoing, and we have delivered new dark subarray reference files for everyone. These do have some residual 1/f noise, and people may have noticed this as well for our regular subarrays. We're hoping to improve that in the future. But that might impact certain analyses, and folks should definitely experiment with turning the dark step off for their actual analyses. But again, we're hoping to update this in December and get 1/f clean darks to everyone as well. In terms of super biases, we did actually see some differences in the super bias for superstripe readout modes compared to the regular subarray. And you're seeing here the differences in the subarray super biases here. And the main thing you'll notice is these strong stripes, right, at each of the edges of the stripes. We're still trying to investigate the exact origin of that effect, but what we understand it to be is just a kind of offset in the pedestal. So we didn't actually see this initially in the extracted frames following ramp fitting because it makes no difference to the ramp fitting itself, but it does make a slight difference to the super bias. These are updated and on CRDS now, so you really shouldn't notice any difference, but just something to be mindful of if you do start seeing strange effects at the stripe edges, although we really don't see those. Okay, moving on. Now, photometric observations. I'm going to quickly go through these. So our first one was a photometric calibration of our photometric standard. This is the standard we use for pretty much all SOS calibrations in terms of photometry. This is BD plus 60. There are many programs available for download for all of this data. And what we've plotted here on the right is a comparison of the observed versus predicted flux for the object relative to the CalSpec model. In black, we have our regular photometric observations, and you'll see these are actually marked as individual points with an error bar. What we're actually plotting here is all of our photometry with our kind of mean divided by the standard deviation. So this accounts for the total dispersion in our photometric measurements over the last few cycles of calibration observations. And then in blue, you can see the spectrum for superstripe, and you can see there is definitely a difference. We kind of match better towards these longer wavelengths, but the shorter wavelengths, we are seeing some kind of discrepancy, roughly 3% between the superstripe spectrum and the regular BD plus 60 photometry. This is something we're going to try and correct for our photometric corrections so that we can account for it for all stripes, but something to be mindful of now if you are interested in getting precise photometry out of SOS, which typically isn't done because we're working with these relative transit measurements. Here's another example for the WST18 data, that TSO, that we were still able to do a photometric correction against in calibration. I'm plotting here the flux against the wavelength. In black, we have the order 1 flux and the order 2 fluxes in blue. We have this nice agreement in the overlap. And again, beyond these longer wavelengths, we know the flux and the overall throughput of the mode is very low. So we expect kind of strong differences at those wavelengths. One nice thing we do see is that we can grab the Gaia spectrum for this source as well. And with a kind of 3% offset, we match very nicely to our observations. So again, a similar 3% offset. So something to be mindful of. And then finally, for the brightest source, we took this bright photometric standard. And actually, the differences here are a bit more obvious and a bit more distinct. So here we have in the plot order 1, 2, and 3 for the actual observation in black, blue, and yellow. Our CalSpec model in red, and then the extracted Gaia prism spectrum in gray. So here you can see some distinct differences for each of the orders compared to our CalSpec model. So that might suggest some kind of effect that's with stripe size or brightness that affects our photometric calibration. And again, something we're still looking into, but we're trying to just give you all a scope of where we're at right now. Okay, finally, to the transit observation. So here we conducted a transit observation of WST18b. I mentioned this is like this 10 Jupiter mass object. It's very heavy. The scale height is very small, so you really don't expect any kind of features in transmission, and this comparable HST wild full camera 3 observation as well. So here are first the HST observations. Those came in first, actually, and were successful. Here you can see the transit itself before any kind of fitting or observation. Looks very clean, both on the forward and reverse scanning. And then here is the light curve from SOS. So again, this is processed using standard pipeline routines. We're not doing anything fancy. This is kind of what the pipeline will give you by default. We did perform some small background modification to utilize our contemporaneous background that was taken with this observation. It doesn't make a huge difference on the light curve itself, but that's available as well. And then we conducted this light curve fit quickly using Juliet, using a very simple light curve fit. So we're not doing any sort of, Gaussian process fitting or any kind of complicated baseline fitting. One thing you'll probably notice here is that there might be some kind of nonlinear trend in the baseline of the transit outside of transit. We think that might be might be a result of the actual thermal phase curve of the planet itself throughout its orbit. So we're not correcting for that either. So there's definitely some improvements to be made there, but at least for this early analysis, we have a big success in that the mode has worked. We've captured this transit and with decent signal to noise as well. And then finally, we've been working pretty hard, and literally this morning we were able to put together our first transmission spectrum measurement, comparing that HST observation with the NIRISS soft observation. So you can see HST in the background in blue and red. We have this 2014 in blue and then this new 2026 observation in red. The first thing you'll notice is actually these blue and these red spectra are highly consistent, which is really nice to see. You can take an observation 12 years apart with HST and get the same answer. However, there was a small offset between SOS and these HST observations of around 500 ppm. Now, there's a whole range of things that could be causing that, down to the different instruments and telescopes themselves. Like I mentioned, light curve fitting that baseline could certainly affect this, whether you use some kind of complex baseline or just a linear trend. So I'm not too worried about this kind of linear offset between the two telescopes at the moment. And you'll see the NIRISS source as well has greatly improved signal to noise compared to Hubble. That's kind of no surprise, right? We have a big 6-meter telescope in space. It's pretty good at observing things. One nice thing I do want to point out is the stripe edge here. So this is where one of the stripe edges ends, just spanning this wavelength range. And here we don't see any kind of significant discontinuity in the spectra that seems correlated with the position that's any different to kind of anywhere else in this spectrum itself. We'll be doing a closer analysis of this at a higher resolution than what I'm showing here. But again, don't seem to be affecting anything at the transmission level. And certainly everyone should be confident, really. I think that we're going to get good observations with the SOS superstripe subarrays. Okay, finally, just to finish off, I want to add some considerations for cycle 6. So here, the main thing I want to emphasize is some updates to the ETC. Particularly, we've updated things to better clarify the superstripe readout times. I know there was some confusion in cycle 5. We've managed to clarify that a little bit by expanding what we record in this exposure time instrument and detector tab. So now the default exposure time for a calculation will be reported as the time to calculate all stripes within the subarray, not just a single stripe. And then there's these finer details that you can really dig into here. The main ones I really want to point you out to is this single exposure time per pixel, and then the single exposure time all stripes. So this kind of shows you how this exposure is actually happening. Per pixel in the subarray that you're reading out in total, you're only getting 20 seconds of exposure time. But over all stripes, it takes 60 seconds to do that, right? Because we have 3 stripes for this sub 680 example. So you have to multiply by the number of stripes. So that's there accessible for you now to help you understand how to conduct the observations and how long they're actually going to take when you put them into APT. The next thing is Pandexo support. So we now have for cycle 6 support for Pandexo for all the superstripe subarrays. So you can go and use your standard routines to calculate what exposure settings you want to have for your transit, how long the transit needs to be, and what kind of uncertainties you're going to get on the transmission spectrum itself. We haven't got to the point yet where we're comparing the transmission spectrum precision we got from the WASP-18 measurement to the Pandexo measurement, but that's something we'll definitely be aiming to do in the coming months. One thing I also want to mention is that in cycle 5, we shared this notebook to assist observers with estimating transit depth uncertainties because we didn't have the Pandexo set up. And I just want to make it clear here that that's not going to be supported anymore or maintained. So folks should really focus on using Pandexo for all of their calculations or their own personal methods. Okay, finally, I wanted to do a quick workflow for selecting a SOS subarray, because I know it can be a little confusing when you have all of these different options available to you. So really your first consideration should be, is your target fainter than a J magnitude of roughly 8.4? If it is, then you should just use subscript 256. That's going to give you the full wavelength coverage. You're not going to lose any kind of photon counting time because of the inefficiencies of superstripe, and you can just do a regular SOS observation. The next question should really be, is it fainter than J of 6.3? This is the saturation limit of that smaller stripe, the standard stripe, the subscript 96, which just kind of chops off the top 160 pixels of the subarray. If it is fainter than that, you need to ask yourself, is there some kind of 0.6 to 1.4 micron order 2 coverage that you really, really want to get? If you don't think that's the case, then you're safe to just use subscript 96, but you might want to consider a dedicated background because you won't be able to estimate the background very easily from the subarray as is. Then if your answer to this is yes, you do really care about order 2, or if you know that your target is brighter than J of 6.3, you need to start asking yourself, is some detector saturation acceptable? There can be sharp discontinuities like Minaza showed for superstripes when you're switching from one stripe to the other. So you want to be mindful of that. Maybe sometimes the best thing to do is accept a little bit of saturation for a big boost in SNR. If you are willing to accept some saturation, you should use the ETC or Pandexo to explore those trade-offs between all the subarrays and make a decision that will really motivate your science case in the best way possible. And if you know, alternatively, that you don't want any saturation at all, you just want a nice clean observation, and you want to use the largest multi-stripe subarray with the largest stripe size that avoids any saturation for you. So again, this will be recorded. You don't need to remember this off the top of your head, but this is a nice flowchart to use if you are wondering which subarray to pick. Okay, just some quick concluding remarks. So first, we've tested these NIRISS multi-stripe subarrays on Sky, and everything went pretty well. We expect the mode to work for all of the future cycle 5 observations. These are going to offer significantly improved bright limits up to a J magnitude of 3.5. So you can observe any known transit host star now without saturation if you'd like to. The data are recorded in this non-standard method where we're reading out these individual stripes one at a time. But our earlier calibration efforts are demonstrating that it's all working as intended, and we have high confidence for the success of cycle 5 programs and the upcoming cycle 6 observations. And then finally, our calibrations are ongoing. You're really kind of getting an early look here. You know, we've only had about a month or so to handle the data and take a look through everything. But what we're hoping to do over the coming months is release a collection of technical reports publicly to everyone that goes into all of our analysis in detail and gives you a real kind of quantitative assessment of how SOS multistripe is performing. Okay, so I'll finish there. One few things I want to just finish on to end is there's some resources here if you want to understand any of these methods a little bit more. And particularly if you have a question, please use the JWST help desk. We will respond quickly, I promise, and we'll get you the answer you need.